So today we're going to be talking about quantum computing in the real world, and you can think of this as an overview. But as Ciprian said, these conversations are not as predictable as other conversations because there's just so much content here. I'm the founder and CEO of security companies, DTS and Pulsar Security. Ciprian, why don't you go into your background, even though you're known to this crowd?
Yep, I'm Ciprian Jichici. I'm the CEO of Genisoft, and I'm the chief data scientist of Soliance. But today I'm just going to be the quantum computing geek, talking together with you, Patrick, about where is quantum computing today, and more importantly, what are the connections of quantum computing with the real world today?
Mm-hmm. Excellent.
So maybe before we dive into the discussion, Patrick, you would like to tell a few words about our very close to our hearts and dear project that we have started a few months ago.
Yes. So we started a podcast called Entanglethings that releases every 2 weeks, pretty regularly, actually. Our first episode was a session similar to this. It was meant to be an overview, an introduction, and then we took the areas that we touched on in the first introduction and we dove into them for the following 6 episodes, and 6 episodes. So that meant episode 7 or 8 was our first guest episode, and we had Richard Campbell from .NET Rocks. And then our second guest episode was Rene Schulte, who has his own Qubits podcast as well. And so we're well on our way, and we're going to be doing topic sessions as well as interviews, and we'll revisit the basics from time to time. So it's how we practice. I guess that's how we practice for talks like this.
In a nutshell, if you folks want to hear us more, us and our guests rumbling about quantum computing, go ahead to entanglethings.com. You'll find a lot of stuff there. And by the way, one of the discussions that triggered this project that I had with Patrick numerous times is, well, what is the real need for quantum computing, right? Like, why does humanity need quantum computing? And one of the things that we came up with is that with classical computing today, we're still more or less helpless in face of problems that exhibit exponential complexity, right, Patrick?
Correct. One of the things that is hard to understand is it's not going to replace classical computing. You're not going to have a quantum computer in your pocket unless your pocket would be very cold if that were the case.
And large.
And very large, yes. So quantum computing can solve the problems that are beyond the reach of classical. And the reason for this, and I mean, there are many reasons, but the biggest reason is quantum computers scale 2 to the n number of qubits that you give us, whereas regular bits just scale based on the number of bits. So it's an exponential expansion over classical bits.
Yeah.
And then we'll try to explain a little of that today.
And one of the things that is kind of like the source of inspiration for probably all of the quantum computing approaches is the way nature actually works, right? If you think about all the things that happen in nature, from starting from the simple evolution of a molecule to the super complex phenomenon that occurs at atom level, planet level, solar system level, universe level, you name it. It turns out it looks like nature actually computes its internal stuff using the quantum approach. That's kind of like the source of inspiration. So I believe, Patrick, this opens like a whole range of potential kind of applicable, very kind of close to real life uses for quantum computing.
Yes. So the analogy I like to say is chemistry is one of the few sciences that really hasn't gotten a huge leap forward by classical computing. Biology, science in the forms of physics, medicine. They've all seen rapid improvement when computing, classical computing, was added to them. We just haven't seen that in chemistry. And there's a talk that Ciprian gave that I saw where he talked about modeling electrons, free electrons. So my laptop is pretty powerful, and yours, everyone who's watching, has probably got a pretty powerful computer. You could probably model water, 10 electrons. Your system could keep track of them. But as the system expands the number of electrons, as the molecule gets bigger, the numbers get astronomical very quickly. And Ciprian has some really good numbers that he's thrown out of, how many electrons it is before all the computers of the world would be insufficient. And it's not 100, it's closer to 50 or 30. And so that's those material sciences, and then hopefully machine learning. When you talk about carbon capture and nitrogen fixation, these are problems that can't be solved with classical computing, and quantum has the hope to actually tackle them because of its ability to go beyond that scaling.
Yeah, and one of the domains that is very close to my heart is obviously artificial intelligence and machine learning. And we already see a lot of very, very interesting discussions, proposals for algorithms, improvements of certain machine learning processes that are either inspired by the world of quantum or are actual quantum algorithms that are applied to this specific field. So what's really interesting here is that we're not only seeing like pure quantum developments, like the build of computers, the creation of algorithms, of languages, and of things like this, but also it seems that quantum is providing inspiration for fields that are currently powered by classical computing that improve the ways that things are happening over there. And if we're talking about an area that is very dear to my heart, Patrick, why don't we switch to an area that is very dear to your heart, right? Yes. And maybe you can provide us with a little bit of insight on what is the potential of quantum in security.
So this is a great topic because it's the reason that most of the governments are actually paying attention to this. So China, the United States, probably in the lead there as far as how much money and interest they're having. And that's because a man named Peter Shor, who's based where I am in Massachusetts, came up with an algorithm that allows you to break an RSA encryption with fairly few qubits pretty quickly. And so we know that the way RSA works, the way what public-private key encryption works is you take two massively large prime numbers, multiply them together, and then that's the basis of your key. And it's reversible if you know the primes, but it's not if you don't, because classical computers just aren't that good at factoring primes. Shor's algorithm allows you to figure out what class the primes are in, which makes it trivially easy for a classical computer to then calculate it by brute force enumeration. And you can break a public-private key encryption in seconds, which means all of our security is at risk. Now, symmetric key encryption, where Ciprian and I share a key privately, is not as vulnerable, but it's still twice as vulnerable as it is to classical approaches. And so it's across the spectrum. Quantum will make us change the way we encrypt data. And luckily, it also provides ways for us to encrypt data that are unbreakable and where we would automatically know if someone's monitoring or listening in. And so it's a double-edged sword. With one hand, it takes away. With the other hand, it gives. Yeah, so it's not only threats, but it's kind of safe to say that it's also opportunities in terms of improving a lot of the processes that we today have in the fields of security and cybersecurity and so forth. And we've seen a lot, Patrick, a lot of discussion around the number of qubits. I mean, we're a few minutes into our talk and we've already talked a few times about the number of qubits, right? Everybody knows that the current race to in quantum computing is
to build up the number of qubits. And probably the first big thing that we need to clarify, and we're trying to do a job as good as we can in clarifying this, is this very important difference between the concept, the two major concepts that are behind building quantum processors, right? On one hand, you have the circuit-based approach, and on the other hand, you have the quantum annealing-based approach. And you will see today, if you look through the news or if you're researching in more depth, you will see that some companies, like for instance D-Wave, they are reporting thousands of qubits, while others, like for instance Google or IBM or the others, will say, okay, we're still in the tens. And there's a little bit of confusion, but it's very easy to kind of diffuse that confusion. The circuit-based approach is the one that actually promises universal quantum computing. So that is the approach that would be, so to speak, the equivalent of classical quantum computing. When it comes to quantum annealing, the quantum annealing qubits and the quantum processors are actually limited to a very, very narrow and specific class of problems, which is the class of problems of optimization. Not to say that that's not hugely important, it is, right? But it's very important to kind of have this distinction, right?
Yes. So for example, the things I talked about with security are in the quantum circuits realm, because you can't do Shor's algorithm on an annealer. That said, both of these spaces are very important. And one of the things to also think about is most people, when they talk about qubits, are juggling a lot of concepts. And so one of the concepts you have to keep in the back of your mind is when we talk about, especially in quantum circuits, when we talk about qubits, there's physical qubits and there's logical qubits. And so because of error rates, you need to distinguish. And often I read an article and I'm like, well, I don't know whether they're talking about logical or physical. So most of the time they're talking about logical qubits. And what that means is you have enough physical qubits to make up for the fact that there's errors. And sometimes there's very high error rates, not sometimes. That's one of the classical problems with quantum computing today. But so you may need thousands or even hundreds of thousands of physical qubits to simulate a single or a small number of logical qubits that will actually do the work. And it's kind of like RAID. So if you're familiar with RAID, redundant array of inexpensive disks, if one of your drives goes down, you know what it was doing because you can intuit based on the others. It's a similar. Peter Shor is actually one of the people that wrote the first paper on how to do error coding in quantum computing. And so it's kind of in that vein. And so that's one of the places you'll see a lot of excitement is when they do that. But right now, difference between a physical qubit and a logical, most of the time, we're talking about logical qubits.
Yeah, and also maybe it's important to highlight, Patrick, that it's incredibly difficult to build that physical qubit because if you think about classical computing, right, the level at which you operate is the level of atoms, right? And keeping a gate, a circuit stable in classical computing is, let's say, a fairly straight proposition. It's not that anymore in a sense that we got to like levels of so much depth with classical computer microprocessors that we actually cannot go deeper because we start to encounter quantum effects, right? That's why you will not see a significant increase, for instance, in the frequency of classic computer CPUs, right? But getting back to quantum, it is very, very difficult to keep that quantum gate stable. And just to give one example, right? Think about it, you try to build it using a photon, one photon, right? Like keeping one single photon isolated from the surroundings of it, right? It's nearly impossible, right? It's very, very difficult. Not impossible, but very, very, very difficult. And that's the reason why we have these challenges.
And that's why they operate at such low temperatures, millikelvin, very, very close to absolute zero, because heat is noise in that environment. It would be like trying to use a classical computer in a magnet factory.
Oh yeah, I absolutely love that analogy, Patrick. I still kind of laugh at it when I remember the first time I've heard it, but it's true. Try bringing your laptop right inside a huge magnet and see whether that laptop still works or not.
My iPad's malfunctioning in this MRI machine I'm in. So.
So let's switch gears a little bit, Patrick, and discuss another very, very important aspect, right? Which is, okay, so it looks like we do quantum annealing processors. We're trying to build quantum circuit processors. Maybe just one more thing to say, currently we're much more successful in building quantum annealing processors than we are building quantum circuit-based processors, simply because they are much more complex. But let's see where we are with the current state of algorithms, right? And it turns out you don't need a working quantum computer to start thinking or even designing and implementing algorithms, right?
True. Yes. Yeah, there are several companies, including Renee Schulte's company, that are taking problems, casting them as quantum programs, running them on simulated quantum computers, and seeing improvements in performance of 8% or more. And they'll see dramatic improvements when they're run on quantum computers as the hardware catches up.
Yeah. And by the way, folks, if you want to catch a glimpse of where we are with quantum algorithms, there's this very, very nice website called the quantumalgorithmzoo.org. I strongly encourage you to take a look at that, and you will be just amazed by the list of algorithms that have been either already implemented or they are being proposed today in quantum. And you already mentioned, Patrick, the factorization algorithm, basically invented by Shor. There's another very important algorithm, which is the search algorithm, or the Grover algorithm, which, by the way, does not provide exponential improvement in search, but it provides quadratic improvement, which is still a significant improvement in terms of performance. But we also see some very, very interesting developments in the areas, and those are again very kind of close and dear to your heart, Patrick, of crypto protocols, like for instance the BB84, right?
Yes. Yep. We have an upcoming episode on that. It's all about, can I share what mechanism can I use these quantum effects so that I can share a key with you and know with a certainty if someone is eavesdropping or trying to manipulate the stream, something we don't get with classical bits. I can't look at a classical bit and say, oh yeah, Nancy read this, I can tell. It's always just a guess, whereas with quantum we can know. And there's many of these protocols. It's a great website to go to understand where we stand with the development of algorithms for quantum.
Yeah, and by the way, remember this, especially protocols like BB84, they build on this fabulous property of quantum systems that you can literally, nature prevents you from reading their state, right? No matter what is the internal state of the quantum system, the moment you measure it, it will collapse into one of its base states. So this means that, exactly as Patrick mentioned, right? Whenever you attempt to read something in quantum, right, the state will collapse, which means that from that point on, everybody will be able to know that somebody attempted to read that state. That is a crucial property in terms of security systems. So maybe now, Patrick, is a good moment to switch gears again and move a little bit into a discussion about who are the most important players in the field of quantum today.
Agreed. And we have about 5 minutes before the Q&A starts, so we're right in the home stretch here. So as you can see from this slide, it really lays out who the players are, and we apologize to any governments, universities, or private companies we've left out of this mix. The private companies are the ones that are getting a lot of the press. Microsoft, Google, IBM, D-Wave, Getty, Intel. There are others. There are others that are doing programming. There are others that are doing algorithms. There are others doing many things, but these are the ones that are building hardware, that are building chips, that are building systems for trapped ions, systems using photons, systems using supercooled circuits. I learned a lot of what I know from Ciprian, who's I consider a mentor as well as a colleague, but I also took the courses at MIT with Peter Shore and Isaac Chuang as my instructors, and so being close to Boston has its benefits. MIT and Lincoln Labs are at the forefront of this stuff, as is all the other universities, Oxford. I just was watching Professor Andrea Melia, and I'm sorry if I'm saying his name wrong, from Australia, talking about some things. So there's brilliance on this topic all over the world, but you'll see a lot in China and the US because those two countries seem to be locked in a arms race for quantum. There's other countries that are trying to participate, all the allies of the United States, Russia and other countries, but you're going to see a lot of activity there, and we're not going to know what they're doing. I'm an American citizen. I don't know what the U.S. government is doing. I'm sure a lot of Chinese citizens don't know what their government is doing other than what's public. And so we don't know what they're doing, but I think that most of the real innovations are happening in the first and second columns here. The universities are pushing discoveries in base science, and the private companies are funding that and taking advantage of it and pushing it in the real world. It's very exciting because we're seeing a whole new computing world being reinvented with knowledge of how classical computing evolved so we can avoid mistakes and bottlenecks, but at a breakneck pace compared to what we saw in classical computing.
And by the way, speaking of that, Patrick, we had an amazing discussion in our episode with Richard Campbell, right? When kind of most of the episode turned out to be a comparison between how classical computing evolved and how quantum computing is evolving. And believe it or not, it's actually, like, for me, it was like a revelation, as a lot of the stuff that happens today in quantum computing kind of is like an indigo repeat of what happened in classical computing, except that what you very well mentioned, Patrick, except for the breakneck pace. So what we did in decades with classical computing, we seem to compress probably in years when it comes to quantum computing. And that kind of leads us, Patrick, to one of the most hyped questions that we see out there, spawning a lot of discussion, triggering a lot of debate, right? So what about this concept of quantum supremacy?
So yes, it's a thorny question. Basically, it's show us an example, a real example where a quantum computer can do something clearly faster than a regular computer. And unfortunately, I think quantum supremacy has been demonstrated with a caveat. It's been demonstrated using the Deutsch-Auser algorithm, which is an algorithm that doesn't do anything except prove that a quantum computer can run something faster than a classical computer. And so it's not satisfying. It hasn't done anything that's useful that is clearly superior. But if you look at just the Deutsch-Auser algorithm, it is scientifically provable, in my opinion, or at least I think it's been demonstrated, that we are going to have quantum supremacy, that quantum will solve problems faster than a classical computer. But people want something like break this RSA key faster with a quantum computer, and we're just not there yet. We don't have enough qubits to do that job. Now, that said, I personally believe the first time you're going to see quantum in every newspaper, on every TV show, is the year, the week, the month, the day, or whenever, when we solve the nitrogen fixation problem. Because I believe that we only need a medium-sized quantum computer, general-based circuits, to solve that problem, and it'll save 1 billion barrels of oil a year, or 1 or 2% of all energy production a year, if we can solve it. And so I think that's going to be the big watershed moment for us.
Yeah, and I think we mentioned that already, Patrick, but we share this belief together that quantum computing is not a replacement for classical computing, right? Quantum computing is a complement to classical computing. So the way we see the world moving forward is we'll see ever more complex and powerful classical computing, right? The race does not stop in classical. The race to build data centers, the race to build more powerful and more distributed classical computing power is by no means over. It's probably just beginning. In the same time, as you mentioned, we're going to see kind of like mind-bending quantum capabilities in computers. And just to leave our audience as the last part of this discussion, before we get into questions, right? One of the most recent papers that is currently under peer review advances an amazing theory, right? We all know SETI, the search for extraterrestrial life and intelligence, right? And this guy here, Michael Hipke, says, what if we were looking at the wrong signal? What if we were searching the wrong signal? What if we should actually start searching for quantum communications in the interstellar space and not a kind of classical type of communications?
That's very interesting. The Drake equation does include in some versions how long a society uses radio waves for communication. And in 100 years, we may not use them anymore. So we should definitely be looking for more advanced communication mechanisms.
Yeah,
that's awesome.
And on that note, folks, we will kind of leave you to ponder and be mesmerized about the amazing kind of opportunities that quantum computing is opening. We thank you very, very much for being with us at this session. So Vlad, back to you for any questions.
Thank you, Ciprian, and thank you, Patrick. It's been quite interesting to find out more about how quantum works and the current challenges in the field. I have a little bit of a question. Now, one of the algorithms you mentioned was the Shor factorization algorithm, right?
Yeah.
Basically, this could be used to derive the private key from a public key, right? From an RSA public key.
Yes.
Knowing that in the early days of Bitcoin, most of the addresses also function, well, most of the public keys also functioned as addresses. And I remember reading a few months ago that most of the original Bitcoins mined by Satoshi were stored in such addresses, so addresses that are basically RSA public keys. Is it feasible to think that whenever somebody gets access to a sufficiently powerful quantum computer, they will be able to steal all those Bitcoins, by reversing the public key and getting the private key?
I think they could. So what you have to understand is it doesn't take a small number of qubits to solve it. So my calculation, and I asked this question specifically at MIT, and I got a, well, it depends answer. So if the key is 1024, which is a fairly weak RSA key, it takes about 3,000 logical qubits to factor that, to effectively factor that. Now, Shor's algorithm it's one of the earliest algorithms we have, and it's been optimized, so you can probably bring that number down, but it's probably never going to get down below 1,500 or 1,000 because the number of bits. We're so far away from that. You still have a few years to move your wallets. So I would advise don't have a symmetric key, have a password. And I know that's mind-blowing, is that passwords are safer than certificates, but in the face of quantum, eventually. Now, again, quantum's a little like fusion, is it's always 10 years away. And 10 years ago, it was 10 years away. I think we've hit the watershed, though. We're starting to see actual hardware. It's not just papers, and it's moved much faster. I believe that in the next 3 to 5 years, we have a shot at solving the nitrogen fixation problem. And if we do, the world will wake up, and the money, which is already staggering how much money is going into this, it's gonna blow the roof off. So I hope that answered. I think the answer is yes. Eventually, quantum will be able to break that, but it's not tomorrow. And if it was, then I would be like hacking right now.
Yeah, I think we all would. Yeah. But that very, very much answered the question. Meaning that, yeah, as you mentioned, we need a lot of qubits, and right now we have some like tens, maybe hundreds. Not sure.
53 is the most official number I've heard from IBM. They might be in the 60s now. The other problem is, as you add them, it gets harder to hold them all together. And so getting from 50 to 100 isn't a twice as hard problem. It's probably I don't even want to give it, but it's not linear.
Yeah, think about it, Vlad. Like the challenge, like the core challenge is, no matter what is the target number of qubits, let's say is 100 or whatever, the challenge is twofolded. One is to keep every qubit stable for a certain amount of time, but the bigger challenge is to keep them stable together in the same period of time, right? Like that is the mind-bending challenge. And when we talk about periods of time, just to be very, very, very clear, like we're talking here about microseconds, right? So quantum calculations happen in very, very short amounts of time. Even so, keeping 100 qubits at the same time interval stable is just kind of like a daunting task. So if you are kind of thinking like, oh, this quantum stuff is hard to understand, then imagine how hard it is to actually build the things that run this stuff that is hard to understand.
I just thought of an analogy. Imagine trying to take a picture of a puppy and now 10 puppies and 20 puppies where they're all looking at you. It's very difficult.
I can take a picture of one.
Or should we say 101 to be aligned with the classical, right?
Yeah, well, I'll keep that in mind while I try to photograph my puppy. Yeah, I have issues with just one, so
exactly. Yeah,
I can imagine
so you're
how hard.
struggling with one qubit, right?
Yes.
Yeah. I'm getting to that.
We hope so.
I also wanted to know. I know there.
Dan's muted.
I'm muted.
No,
Dan was muted. Yeah.
I was going to say doing it with all of them individually and then using Photoshop doesn't work with the qubit.
No.
Unless Adobe comes up with something like Photoshop for quantum.
Yeah.
That's probably going to be an in-app purchase or something like that.
Yeah.
I wanted to ask, do you think, given the state of quantum development at the moment, do you think we should try out some of those emulators, sharpen our skills, or is there still time and we'd better focus on something else?
Honestly, the reason I got into this, other than the security aspects, is I think that even if it takes 10 years for quantum to reach its middle prime, not even its late prime, we're going to have to run as fast as we can to understand the math, the science, and I don't mean to scare people away. So I have 18 credits of calculus from college. I have an engineering degree. I took a lot of calculus. And while I was taking the MIT course, it was only a 5-hour-a-week course for 8 weeks, but I was spending 10 to 15 hours a week reviewing math so I could really understand everything. And I probably went overboard, but I revisited linear equations and the fundamentals of calculus and how to do, imaginary integrals and crazy stuff that I still think I might have been dreaming some of it. So understanding the physics isn't technically required, but I think it's required. And so it's not like picking up access after having worked with SQL. It's like learning a language that is alien, completely alien, and you have to understand the social cultural cues of an alien culture. It's interesting, but it can be daunting if you really want to understand it. Now, Ciprian and I have had this conversation. We think that it's going to be abstractions layered on top of it, so you don't need to know as much, but you still need to understand quantum parallelism, quantum interference, how things can work, and a lot of it defies the logic of the physical world, which means you're dragged into quantum physics, and that's where it's going to be, because otherwise you'll be sitting there and like, I don't know what to do next. I don't know how to get from the tools I have to solve the problem I have, and we need that. We need people to do that. So I do think it's a longer road, but there's plenty of tools out there. There's Microsoft has the Kata for QSharp. IBM has a ton of tools. There's Qiskit. There's just plenty of tools out there to get people started, and you can start writing code today.
Yeah, it's funny that you mentioned this, because one question from the audience just popped up. What do you think about QSharp?
I think it's wonderful. I mean, Ciprian, you started with QSharp before I did.
Yeah. Well, think about it like it's for those of you who are like me and Patrick, slightly kind of older in the field. It's pretty much like it was in the old days with assembler, maybe not even there, right? From the level of abstraction. And one interesting thing I believe, even if quantum computers are going to be a thing, in order to become a mass thing, to have the same ecosystem developed around them, like with classical computer, we need to work on the abstractions, right? Understanding the way quantum gates operate is not going to help quantum computing become a mass thing, right? We need to build layers of abstraction, and this is where I believe Microsoft, for example, is doing a great job with the whole ecosystem, the emulators, as well as the language. But the language itself, it's still, if you look at it, it's still operating with the concept of qubit, right? It already has significant abstractions added to it, but it still blows your mind. Right, like Vlad, you are an MVP in AI, right? Imagine implementing a deep neural network today using the assembler language, right? So
there we are.
Like honestly, this is where we are today. Like even the simplest task with QSharp and quantum computing are very comparable to this theoretical example that I gave. So we definitely need a lot more work in kind of raising the level of abstraction, even if we are running on simulated. So you know, on your local laptop, you have enough computing power to simulate maybe 3 or 4 qubits. But if you kind of fan out into some public cloud resources like Azure, you can already move up to simulating maybe 10, 12 qubits. Now with 10, 12 qubits, you can already write algorithms and programs who are really quantum algorithms and quantum programs. So we don't need to wait. We can already do this work in parallel with the folks who are kind of doing those wizardry magic things to build the physical devices.
And there are already some building blocks. So for example, the Google language, CIRQ, they have a function call for Shor's algorithm. So you just pass in the number that you want to factor, and it'll run Shor's algorithm against it. You probably can only do it for 15 or 21. Those are the highest primes it'll work with because of the computing power. But we're getting there. And underneath there, inside of Shor's algorithm, is a Fourier transform done in quantum. So Fourier transforms are a building block because you don't have to know which gates to use to get one because someone else assembled it. But again, that's still very early days.
So basically, you have the chance to either wait until the tooling is there or to build it yourself, and then be part of the change.
Be a founding member of the quantum computing world.
And just so to be clear, it's never too early trying to understand the fundamental concepts of quantum, because when it will take the world by storm, right? So just make no mistake about it. It's not replacing classical computing, but it's going to open a whole new world of computing, probably way larger and way more complex than the one that we have today with classical computing. So,
but like every drug, I'm going to give you the warning. The warning label is learning about quantum computing may cause you to spiral in YouTube for days. And you may not be able to get any work done for a few days because your mind is so blown. I had two security engineers who literally did no work for almost an entire week because they were so blown away. And so, but how can that work that way? That doesn't make any sense. And eventually they came back down to earth, but they were converted.
Now that's a fair warning, Patrick. I fully second that.
Wait a minute. It does what? How can there be more light after there's not?
Well,
you know,
and by the way, folks, the one question to avoid, that's the one that I learned myself the hard way. The one question to avoid is the why, right? Yeah. Like keep that all the way, like the last question that you ask about quantum.
You can ask that one in church.
Yeah,
but don't ask it.
Don't ask yeah, why is this even possible, right? Because the moment you start asking the why, you're gonna spiral into something that it's very difficult to get out of, right? Let's keep it like it's still one of the mysteries of the universe.
Yeah.
We have another one. Well, thank you very much, gentlemen. I know we went a bit in the break, but I think it was well worth it.
Thank you very much.
Again, thanks a lot. It was wonderful having this conversation, and yeah, hope to see you next time.